The last thing we're going to look at in this unit are reactions that occur at the benzylic position. And I'm not talking about reactions that happen on benzene. That's actually the next chapter where we'll go into that, or our next unit. And what we're going to look at are the reactions that happen at the benzylic position. So the first of these is oxidation of the benzylic carbon. Using a strong enough oxidizing agent like chromic acid or potassium permanganate, that benzylic carbon will get oxidized to a carboxylic acid. Now here's the catch. The benzylic carbon must have at least one hydrogen on it in order for it to be oxidized. And so, for example, if we have something like this, this benzylic carbon right here has a hydrogen on it, has one. This one here has no hydrogens on it. So that benzylic carbon with a hydrogen is going to get oxidized. The other one is not. Now, notice what happens is all the rest of these go away. You say, where are they? What happened to them? We don't really care. You know, if it was one carbon or a chain of 50, like they're just all gone, and all we have is a benzoic acid in the end. Now, the next reaction that's important to know, and you already kind of know this one, but radical halogenation at the benzylic position, if we use, like, for example, NBS in peroxides or Br2 in light, the benzylic position is preferentially halogenated over any other ones. So you're never going to see that bromine end up on benzene under these reaction conditions. We will put bromines on benzene. That's for the next unit, though. But we don't do that in this method. A radical halogenation will specifically halogenate the benzylic carbon and no other carbons. Now, one final reaction I want to look at, and this one does pertain to reacting benzene. Benzene's fairly unreactive to a lot of things, but we can reduce it. We can add hydrogen to this in a similar way to what we did with alkynes when we did the dissolving metal reduction. Here we're going to do something very similar with sodium, metal, and ammonia. We're just going to toss in some methanol. And that's going to do what's called a Birch reduction. And that's simply going to make benzene into a non-conjugated diene. Where this gets a little tricky is when we have substituted benzenes. Because depending on whether the group on benzene is an electron donating group or it's an electron withdrawing group, that non-conjugated diene will end up in various orientations. So if it's an electron donating group, then this is the only product observed. This one is not observed. And if it's an electron withdrawing group, then this diene is observed, not the other one. So that's the only thing to watch out for. So you will definitely want to review your electron donating groups and your electron withdrawing groups. You're going to see those. I mean, they popped up last unit, they popped up this unit. They're going to pop up in the next unit when we start talking about reactions of aromatic compounds. It's very, very important that you have that list just committed to memory of the common electron donating groups and common electron withdrawing groups.